Good morning, everyone. So this week, our challenge is to cover 3 chapters in one lecture. So before I start, I just want to point out that each one of these chapters, chapter 12, 13, 14, had about 50 slides. So if we put those all together, that would be 150 slides. Nobody wants to listen to that. So what I did is I edited it down to 40 slides, 39, I think. Which, I think is appropriate for this class, first of all. What I want to try to give you here in this PowerPoint lecture is sort of a very surface level understanding of how the pulmonary system functions. And then, as this is an exercise physiology class, we're going to mostly focus on what happens when we exercise, how the pulmonary system contributes, and then touch on some testing and diseases that are associated with the pulmonary system that can have a negative impact on exercise performance. And then our lab this week is going to be looking at one of the most common pulmonary tests, which is known as the forced vital capacity test. And we'll talk about that a little bit more as we go. So before I start again, just keep in mind that I kind of smushed this together to compress it as much as possible to give you sort of a surface level understanding of the pulmonary system. As you progress in your college careers, you might take an anatomy and physiology class where they will build on this more and you'll get a more in-depth understanding then, okay? So let's talk a little bit about some anatomy and physiology of the pulmonary system in general before we get into how exercise affects it. So ventilation essentially refers to the process of moving air in and out of the lungs, okay? And the air we're talking about, we call it ambient air, which basically just means the air around us, okay? As you know, air comes in through the nose and the mouth, passes down through the trachea, okay? As that process occurs, the air that we breathe in is warmed close to our body temperature in the trachea, okay? It can also be filtered, so especially when we breathe through our nose, a lot of particles are filtered out of the air, so they do not enter into our lungs, okay? The air is also humidified at that point as well, so moisture is added to the air. And then it enters into the lungs, going into what we call down the bronchioles. So we have two bronchioles that kind of split into the 2 lungs, right? And then ultimately in the lungs, the air goes into what are known as the alveoli, which are like the individual air sacs. It is in these air sacs that oxygen is transferred from the lungs into the blood, at which point then oxygen is delivered to the tissues. So within the alveoli, these individual air sacs, that is where the gas exchange occurs. O2 moves from the lungs to the blood, and then CO2 moves from the blood back into the lungs where it can be expired, okay? That's sort of the anatomy and the physiology, basic physiology of how ventilation occurs. And here are some of the structures. So again, here's the trachea, which we may more commonly refer to as the windpipe. That's where a lot of the warming occurs, the humidification, etc. The bronchioles are not necessarily shown. Well, here we can see them. Individual bronchioles, right? So we have our main bronchi, which splits in half, and then we have these individual bronchioles. It's sort of like a tree, right? You have the bronchi is the trunk of the tree, and then the branches split off into what we would think of as the bronchioles, right? And then at the end of each bronchiole is an alveoli. So think of the alveoli as the leaves on a tree, right? They're sort of the terminal end. And that's actually very symbolic for what's occurring with trees because the leaves absorb the CO2 and convert it to oxygen, right? So it's kind of very symbolic that our lungs look a lot like trees. I've never really thought of that before, but that's kind of amazing thing to consider, actually, right? So again, at the end of the bronchioles, we have the alveoli. Here are some pictures that show us, you know, like this kind of represents an alveoli here. So, or sorry, down here. Oxygen is transferred from the alveoli into the blood, okay, where it can then be directed to the rest of the body. And we would call that oxygenated blood, okay? And then CO2, which is coming back from our veins, also passes by in the pulmonary veins. The blood passes by and drops off CO2, right? So we're dropping off the waste product, which we expire, and we're loading oxygen into the blood here as well, so it can be delivered to the tissues where it can be used for energy production, okay? And that occurs in the blood vessels that we call capillaries. So you probably heard of capillaries before. I'm not going to talk about them too much now because we'll get into those more when we get into the cardiovascular system. But just to kind of quickly say this, arteries and arterioles transfer oxygenated blood. Capillaries are where the gas exchange occurs. And then on the other side of the capillaries, we have our venules and veins, and those carry deoxygenated blood, right? Often those two types of circulation are color-coded as red equals oxygenated blood, and the blue is deoxygenated blood. Red having more oxygen, blue having more CO2, okay? One other thing to acknowledge is by having so many of these alveoli, right, there's a lot of them, the surface area within the lungs that allows for gas exchange is gigantic, right? So what they show here visually is the space that we have available for gas exchange is actually equivalent to the size of half of a tennis court, right? So if we took all of our alveoli out of our body and laid them out flat, we would cover the half of a tennis court, right? So we have a massive amount of area available for gas exchange. We often say that the lungs are overbuilt, which means in a healthy person, you will never need the amount of surface area that you have available for exercise, okay? Now, once we start having lung disease present, then that can be compromised, but in a healthy person, the lungs will never be the limiting factor. Some other system, like the cardiovascular system, the muscular system, will be the limiting factor prior to the pulmonary system because we have so much surface area available for gas exchange, again, in a healthy person, okay? So how does breathing actually work? It's kind of cool, I think, is that breathing really works through alternating pressures. Now, usually the air around us has an air pressure of 760 millimeters of mercury. That's sort of your basic atmospheric pressure in Earth, okay? Through the actions of our diaphragm, either contracting or relaxing, the pressure within our lungs can move slightly above or slightly below, sorry, I went backwards, slightly above or slightly below atmospheric pressure, okay? So kind of take a look at this picture here. When the diaphragm contracts, it drops. And what happens is the pressure in our lungs drops below atmospheric pressure. So for sake of argument, let's say when the diaphragm contracts and descends, the pressure in the lungs drops to, let's say, 756 millimeters of mercury, okay? Now, according to a law that we'll look at later, gases always move from areas of high pressure to low pressure, okay? So with the pressure dropping in the lungs as the diaphragm contracts, air is going to be driven from the atmosphere, where it's 760, into our lungs, which is 756, again, moving from high pressure to low pressure. As that occurs, our lungs expand, okay? Which drives the pressure in our lungs up. And then the diaphragm relaxes, allowing the diaphragm to move up. And again, that would increase the pressure in our lungs. The lungs are full, diaphragm then contracts. Now all of a sudden it flips. The pressure up here is still 760, but now the pressure in here is 764. And again, because gases move from high pressure to low pressure, the air is driven out of our lungs into the sky. So the diaphragm is very much sort of like the main muscle involved in helping us breathe. Okay, again, diaphragm drops, pressure drops in our lungs, that pulls air in. We call that inspiration. Diaphragm rises, pressure goes up in our lungs, that drives air out. We call that expiration. Now, personally, I find it fascinating that just goes on literally all the time, and we don't even think about it, right? That's just happening. So we have this autonomic control of our diaphragm kind of being stimulated to contract and relax. It doesn't happen under conscious thought, although we can influence it if we want to. But there's different things that speed it up. And as we'll see when we exercise, the rate of contraction of the diaphragm actually is sped up, and that allows us to move air in and out faster, which is required when we're exercising. Okay. We also have the actions of the ribs that assist in this. Okay. When the rib muscles contract, the rib cage opens up, and again, that aids in dropping the pressure in the lungs and pulling air in, right? Then, as the muscles in the ribs relax, rib cage closes, and that drives the pressure up and forces air out. So notice that we have both of these actions occur to reduce pressure in the lungs, and we're talking about air pressure, and that pushes air in, okay? And then both of these actions work to increase pressure in the lungs, which drives air out, okay? So that's kind of the basics of how ventilation, or breathing, as we simply put it, works. So then once we have the oxygen in the lungs, again, it ultimately travels down to the alveoli. And what occurs there is what we call diffusion. Okay, so the gases are going to diffuse, much like we said, gases move from areas of high pressure to low pressure. Diffusion always works according to Fick's law, that gases diffuse from areas of high concentration to low concentration. So if we jump back here really quick to this slide, there's a high concentration of oxygen in the alveoli, low concentration of oxygen in the blood. Therefore, by the law of diffusion, that gas is going to move here, right? And then the opposite occurs here. High concentration of CO2 in the venous blood, low concentration of CO2 in the alveoli, so that gas is going to diffuse from high concentration to low concentration. The pressure and concentration gradients, we call it, they really control the whole pulmonary system. Things always move from high to low, either high pressure to low pressure, high concentration to low concentration. And that drives our breathing essentially, especially at rest, almost exclusively. So these next couple slides kind of go through the different steps in inspiration, which I already sort of went through a second ago, but just make sure you maybe pause this real quick, take a second to read these steps for inspiration. It talks about how the diaphragm and the rib muscles affect the pressure, and then we have expiration occurring here, right? So just again, pause this recording, take a minute to read this slide and this slide on your own as we'll move on to the next one. So let's talk about the air around us. Now this is something that we've already talked about a little bit. the air around us has sort of a basically a fixed concentration of the different gases, okay? So the air around us is composed of 20.93% oxygen. Remember, we talked about that when we were talking about calibrating the metabolic cart, etc. And it only has 0.03% CO2. So just thinking about that alone, right? In our lungs, the concentration of oxygen is less than this, which again drives oxygen from the environment into our lungs. And in our lungs, the concentration of CO2 is higher than this, and that drives CO2 from our lungs to the air, right? And that basically, again, sort of forces that alternating concentrations. Things always move from high to low, and that again helps to drive respiration, okay? I don't really want to say anything else about this slide, but really just pointing out again the concentrations of oxygen in the air around us and the concentration of CO2 in the air around us in the atmosphere. I'm trying to think if I even want to introduce this slide to you all at all. I guess we will. We've talked about, the barometric pressure, atmospheric pressure is 760 millimeters of mercury. That's of all the gases: oxygen, CO2, nitrogen. Now, if we just took out oxygen, the pressure of oxygen alone is 159 millimeters of mercury, right? So if we go back, atmospheric pressure, 760, and that's all three of these gases together. If we just took out the oxygen, 20.93% of that 760 would be 159, okay? So again, in the atmosphere, we call that the partial pressure of oxygen. The partial pressure of CO2, look, is still very low, 0.02, okay? And in a second, we'll see what the partial pressure of those gases are in our lungs. And again, we'll just have a better understanding of how this concentration gradient drives oxygen in, CO2 out. Again, this slide essentially restates something I've already talked about. So pause it, take a second, read these bullet points. And here's the good slide where I was kind of talking about the pressures. So notice, let's see, in our lungs, in an alveoli, here are the pressures of oxygen and CO2. So the partial pressure of oxygen in our alveoli is 100, while the partial pressure in the air is 159. Sorry that keeps happening. I don't know what's doing that. So again, as things move from high pressure to low pressure, the partial pressure of oxygen is higher in the air, lower in our lungs, and that's going to drive oxygen in, right? On the flip side, the partial pressure of CO2, 40 millimeters of mercury in our alveoli, 0.3 millimeters of mercury in the environment. Therefore, CO2 is driven out as the gas moves from high concentration and pressure, here, CO2, to low concentration and pressure in the air around us, okay? So I think that really simply summarizes how the pulmonary system works, right? We have these alternating high and low pressure situations that drive oxygen in and drive CO2 out. Don't worry too much about these other numbers that go around. They're just kind of subtle variations. One thing I will point out, though, is that in a muscle, the partial pressure of oxygen is 40. In that arterial blood, partial pressure of oxygen is 100. So again, that's going to drop oxygen from the blood into a muscle, right? again, high concentration to low concentration. Partial pressure of CO2, on the other hand, is higher in the muscle, so it's going to drive the CO2 out. So it can go up to the lungs and be expired. Okay, now, as I said earlier, in a healthy person, the lungs are never a limiting factor. We have so much capacity in our lungs, your average healthy person is never going to take full advantage of it. There are diseases, there are impairments that can exist, which will have a negative impact on the lungs. We see a couple listed here, right? If the alveolar membranes, so the alveoli, get some, what do we want to call it? Like, they get kind of gunked up, right? They get pollutants, nasty stuff that layers them. That's going to reduce, and that's going to limit gas exchange. And that's going to reduce the surface area for diffusion, right? And that could ultimately have a negative impact on the amount of oxygen that gets into the blood, right? Just think for a second about a lifestyle habit that people may have that could introduce a pollutant into the lungs, and that pollutant starts to sort of coat the alveoli and thereby reduce the amount of gas that can diffuse through. Can you think of anything? If you thought of smoking, that's what I was indicating, right? When you smoke, you're bringing in a lot of different pollutants, but tar is one of them, which, if you know what tar does on a road, right? It coats it and makes it kind of sticky. Well, think of that occurring inside of your alveoli. And once that tar is built up in there, if you keep on putting it in, it's never going to get removed. Now, if you stop smoking, your lungs have a really amazing ability to recover. Within weeks, you'll start to see improvements in removal of that pollutant, that layer, so your alveolar function can return. But as long as you keep doing it, your alveolar capacity will be reduced because of that surface area that we saw previously was as big as a tennis court. With smoking, it kind of slowly starts to shrink, and your ability to bring oxygen in and get CO2 out becomes compromised to a certain extent. Okay? And how does that affect performance? Well, if you can't get as much oxygen in, that's going to have a negative impact on your ability to exercise, right? So I'm sure you all know somebody, or maybe you even, I don't know, who smokes. Their capacity for exercise is usually less than someone who is a non-smoker. Now, if the smoker is an athlete, they might be able to overcome it. But if you kind of just take your average person who's not an athlete and you make them go jog around the block and they smoke, they're going to be excessively fatigued because their body just can't get in as much oxygen as somebody with healthy lungs. All right, so let's talk about how oxygen is transported in the blood quickly. Two ways. Some of it is dissolved in the blood and just kind of is carried in the blood freely, okay? But the majority of it, the majority of oxygen, is bound to a protein that is called hemoglobin. Hemoglobin is found on red blood cells, and over 80% of the oxygen that is carried in our blood is bound to hemoglobin. So I was a little off, 60 to 75 times more oxygen than what is dissolved in the plasma, okay? There's really nothing on this slide that you all need to know or I'm going to ask you about. But again, that pressure sort of drives the oxygen from the lungs onto the hemoglobin. Okay, hemoglobin has a very high affinity for oxygen. So when oxygen is there, the hemoglobin is going to kind of suck it up like a sponge, right? And that's how the oxygen gets transported in the blood. At least the vast majority of it is bound to hemoglobin. Now, there are conditions that can affect transport capacity. Anemia is a condition where there is a lack of iron. And I didn't mention this, but hemoglobin is an iron-containing protein. So if somebody has low iron, that can have a negative impact on their ability to produce hemoglobin. And if hemoglobin is compromised, then oxygen carrying capacity would be compromised as well. There are many reasons why you could have anemia. There could be some, you don't eat enough meat. Meat contains a lot of iron. So somebody is found to have low iron, they're often encouraged to eat more red meat. There's also a congenital, what do I want to say? There's a sort of a hereditary condition where somebody may have reduced iron deficiency. And again, that could have a negative impact on, as we see here, their capacity to carry oxygen, which would mean even the ability to sustain mild aerobic activities could be difficult because of that lack of oxygen carrying capacity. So as we've talked about in the past, or even today somewhat, this kind of gives us an indication of how gas exchange occurs at the level of a muscle, right? So we have the arteries. Arterial blood delivers oxygen-rich blood here. And then imagine that these capillaries surround a muscle, right? So it is in the capillaries that this gas exchange occurs, okay? And then the deoxygenated blood, it's called, leaves and travels through the veins back up to the lungs, where again we have gas exchange occur again. Gas exchange occurs at two places, in the lungs and then at the tissues, okay? And we call that difference that exists in the arterial blood and the venous blood the AVO2 difference, which we talked about in a couple previous lectures, okay? So notice at rest, the AVO2 difference is 4 to 5 milliliters, meaning not very much oxygen is taken out of your blood at rest by various muscles because they don't need as much, right? During exercise, though, we see that the number gets bigger, right? So what does that mean? If we go from 5 milliliters to 15, that means more. Look, actually, this might be the key thing. We have 20 and 20. Over here, we still have 15 milliliters of oxygen. Down here, we only have 5. So what that means is we've taken more out, which makes sense. During exercise, our muscles have a greater need for oxygen, so more oxygen is taken out of the blood for use by the muscles, resulting in less oxygen being found in the venous blood as it exits the tissues. At rest, we don't need as much, so very little is taken out, which means there's more oxygen remaining in the venous blood as it heads back up to the lungs, okay? And what this bottom one is showing you, this is intense aerobic exercise. This is sort of like maximal exercise. So you notice how the number is even smaller in terms of what's left, and the number is even greater in terms of what is being taken out. The higher the intensity of the exercise, the more oxygen we're going to extract from the blood to use in the muscles that are producing the activity that we're doing. Okay, now one more protein to mention. Hemoglobin carries oxygen in the blood. Myoglobin is very similar to hemoglobin, except it works in the muscle. That's why it's called myo. Myo is the prefix that means muscle. So myoglobin carries oxygen in the muscle, right? So oxygen cannot travel on its own within a muscle. It has to be carried by something. And myoglobin is, again, what the protein is called that carries oxygen in a muscle, okay? What we see with, I think I might have touched on this in the previous lecture as well. One of the adaptations to aerobic exercise is we increase the concentration of myoglobin in trained muscles, which means you have a greater capacity to move oxygen from the cell wall into the mitochondria. The more rapidly you can do that, the higher the exercise capacity will be for that individual muscle and the person as a whole, right? So myoglobin, hemoglobin stays pretty fixed regardless of fitness level. Myoglobin increases with fitness levels, and again, that's one of the factors that leads to improving your VO2 max is myoglobin increases. All right, let's see where we are here. All right, this is a very dense PowerPoint. Just to quickly touch on CO2, how is CO2 transported? In a similar way, CO2 can travel freely in the blood dissolved. It can also combine with hemoglobin as well. So hemoglobin can drop off oxygen and then pick up CO2, take it back up to the lungs. Then the CO2 is offloaded, oxygen is reloaded, and we just have this cycle that goes around and around and around, right? We also saw a couple lectures ago that bicarbonate is in our blood as well, and that can also transport CO2. So we have a few ways that we can move CO2 from a muscle where we want to get rid of it, ultimately to the lungs, which allows us to get rid of it. As they say here, it escapes through the lungs. All right, so I want to just kind of switch gears a little bit and notice, I kind of talked about how there's like this auto-regulation of breathing that luckily allows it to occur without us even thinking about it. But here we see a few factors that can influence breathing. And these are really important for exercise, okay? So let's actually start with this one. This is a simple one. As our body temperature increases, that stimulates our breathing rate to increase as well. Okay. So yes, being outside in the heat would raise our core temperature, but as we talked about before, exercising increases our core temperature. So that's sort of a signal to our brain that it needs to increase our respiration rate, right? So we start breathing faster and deeper. That brings in more oxygen and gets out more CO2. Secondly, here we have these different receptors that we call proprioceptors. They're sensitive to changes in muscle length and tension. When our muscles are being used, contracting and relaxing as they are done during exercise, these proprioceptors send signals up to the brain, specifically to what we call the respiratory control center, which is found in the medulla. And that also then would stimulate the ventilatory muscles to start increasing their rate of contraction. So the rib muscles, which we call the intercostals, and the diaphragm, they start contracting more rapidly. And again, that helps us bring in more oxygen, push out more CO2. We have chemoreceptors in our heart, right? When the heart starts beating faster, as it does during exercise, that also stimulates the breathing to increase. We have these peripheral receptors, which means away from the middle part of the body, that are really sensitive to the chemical state, right? So when our blood chemistry changes, that can stimulate increased ventilation. Now, what is something that can change our blood chemistry? Well, for our purposes, the chief thing is lactic acid, right? When lactic acid is being produced in a muscle and sent into the blood, that change in blood chemistry is perceived, and information is again relayed to the medulla, which would then stimulate the ventilatory muscles to start increasing their activity, and that would accelerate breathing, right? So specifically the hydrogen that is found in lactic acid, these receptors are very sensitive to that. And when higher levels of hydrogen are detected, or CO2 as well, in the blood, that information is relayed to the brain, and the brain then automatically increases respiratory activity so we can bring more oxygen in, get more CO2 out, right? So really, all of these things here are really important during exercise. The simple act of exercising tells your brain, okay, start breathing faster and deeper. So these things, as we said, chemoreceptors is a word that I didn't say, but it's kind of what I was indicating was going on here. We have these receptors that are sensitive to the chemical environment in a specific area of the body, and they give feedback to the brain about how respiratory activity should be regulated. A couple specific ones we have that are located here in our carotid arteries. They're called the carotid bodies. They monitor different things going on in the blood that is being fed to our brain. Obviously, our brain is our most important organ, right? The body puts a priority in making sure plenty of oxygen is getting up to our head. So this area is very carefully monitored. So any changes in pressure or chemical environment in the blood vessels that supply our brain will cause some sort of a change in our ventilation rate if necessary, right? That's all we want to say about that. Again, you might want to pause this recording real quick, read through these slides. I'm going to move on as we're kind of running long on time here. Same thing here. I've sort of already touched on this, but again, small changes in chemistry, the concentration of CO2 and hydrogen out in the body can have a major impact on our respiration rate, and that feedback is constantly being given to our brain so adjustments can be made in respiratory activity. Okay, so let's shift gears to exercise. There's a couple volumes of air we're going to talk about now that are important. So the first one is what we call the VE. So this stands for minute ventilation, okay? And what this means is, what the VE is the amount of air that is moved in and out during 1 minute of time, okay? During exercise, light to moderate exercise, VE would increase in a linear fashion, which means as our exercise intensity increases, our volume of expired air is going to increase as well, okay? VE mainly increases as we have increases in what are known as tidal volume, which is what we'll talk about in a second. But mainly, your VE increases not because you're breathing faster, but it's because you're breathing more deeply, right? And we'll talk about these lung volumes here in just a few minutes. And we'll kind of come back and circle back to this, and it'll make a little bit more sense. But I guess really for right now, the take-home point is, as soon as we start exercising, our volume of expired air is going to start to go up because, again, due to all these things that we saw on this slide, really all of these slides, there's a need for more oxygen. There's a need to get more CO2 and hydrogen out. Therefore, we're going to start breathing more deeply. Oops, I went too far ahead. Pause and read this, but I'll just say a couple things first. pH sort of reflects the acid-base balance in our blood, in our body as a whole, right? Human life can only exist in a very narrow pH band, okay? If pH gets disturbed too much, first we would experience some very negative symptoms, but ultimately we could die, okay? So regulation of pH is very important. Hydrogen and CO2 increasing can really throw pH off a lot, right? So the reason why our respiratory system and our cardiovascular system are so sensitive and responsive is because we want to mitigate or minimize the change that occurs in pH, okay? Exercise, therefore, poses a very significant challenge to pH, right? Because we're producing so much lactic acid. We're producing a lot of CO2. But in a healthy body, we can easily manage it because our respiratory system and our cardiovascular system are so responsive, and they have such a great ability to adapt in that moment and help us get out all that CO2 that's accumulating and bring in more oxygen to sort of minimize the change that occurs within our pH, okay? We may come back and talk about pH in a later chapter, but we're going to not talk about it anymore now. But again, you might want to pause real quick, read these bullet points, and then I'll pick it back up when you hit play. Okay, so let's talk about some lung volumes. This is going to be important for our lab. The 4 key static lung volumes we see listed right here. Tidal volume, let's start with that one. We abbreviate this one as the TV, okay? What this refers to is the air that is moved in and out in one breath, one resting breath. So I want you to close your eyes for a second, breathe in a normal breath. So since we're all resting, that was a pretty small volume of air. And it's equivalent to about 0.4 to 1 liter, depending upon your body size. The bigger you are, the larger your lungs will be, the more air you're going to move in and out per breath. The smaller you are, the opposite, right? So TV, that's an important volume, amount of air moved in and out with one resting breath. Then we have our IRV, Inspiratory Reserve Volume. What this represents is the amount of air we could bring in if we wanted to maximally inspire, right? In a normal breath, we only inspire a small amount. Try it again. Okay, now if I wanted to, after I do that normal inspiration, I could fill my lungs with air, right? So I have a huge sort of reserve capacity that if I need to bring in more air, I can, but at rest, I do not need to, right? That volume is large, 2.5 to 3.5. This volume is the most directly related to your lung size. The bigger your lungs are, the bigger your inspiratory reserve volume will be, okay? Now, when do we utilize this, right? We utilize it during exercise. That's why it's important. During exercise, we're going to need more oxygen to be brought in. So we have this reserve volume that is there when we need it. At rest, we don't need it. We can bring in a little bit of oxygen, blow out a little bit of CO2. But during exercise, we need to bring in a lot more oxygen so we can fill our lungs with air. Now, on the flip side, then we have our ERV, Expiratory Reserve Volume. Now, again, in a normal resting breath, we don't exhale all of the air from our lungs. If we wanted to, after that normal expiration, we could expire everything else. So let's do it together. Right, so I could forcefully blow all the air out of my lungs if I wanted to. We call that the ERV, Expiratory Reserve Volume. That's smaller compared to the IRV, 1 to 1.5 liters, okay? But again, during exercise, as more CO2 is entering our lungs, coming from the tissues, it's advantageous to be able to blow out more air per breath to get more CO2 out, okay? So again, during exercise, we utilize both of these things. Now, there's one more volume that we can't really practice. We call that the residual volume. The residual volume is the amount of air that remains that you cannot blow out, okay? So even if I blow out as much air as possible, I'm still going to have some air in my lungs, and that's called the residual volume. So here we see the volumes. About a liter, so 1.2 for males, 0.8 for females. Again, the difference is based upon the fact that males usually have larger bodies and larger lungs. The purpose of that is to keep our air sacs, our alveoli, inflated. If we blew out all of the air from our lungs would collapse, and that would be bad, right? So there's air that stays in the lungs to make sure, it's like a balloon that you want to keep blown up a little bit. If you let that balloon collapse all the way, it's going to be harder to blow it back up. But if you keep a little air in it, then when you blow it up, it's easier to blow up. So that residual volume exists to keep our air sacs inflated somewhat, okay? But again, we cannot blow that out. All right, so this is a graph that I like that kind of shows these 3 volumes. So the 3 that we can manipulate, tidal volume, IRV, and ERV, we call that the vital capacity, or the VC, okay? Notice that vital capacity does not include residual volume, but if we took total lung capacity, that includes the residual volume, okay? Now, since we cannot expire the residual volume, we cannot measure it. We can, however, measure vital capacity, and the vital capacity is a test that we use to assess pulmonary function. So we cannot measure total lung capacity because we cannot measure residual volume. We can measure vital capacity by doing a forceful expiration. That can show us what our lung capacity is because we can measure the volume of air that we blow out in a maximal expiration. Okay. Before we get to that, let's look at a few volumes. Again, comparing males and females. So you see the difference here is males typically have a higher value across the board. And again, that's mainly due to the differences in lung size. Okay, so let's talk about that for a second. Generally, males have larger bodies. Okay, we're also usually taller. Height greatly influences lung volume. Okay, the taller you are, the longer your lungs are. The longer they are, the higher their volume is, right? There's also anatomical differences between males and females that can lead to more room for lungs versus less room for lungs, right? So there's anatomical differences that sort of account for that, but then there's also the body size issue that again, typically males have higher volumes across the board. Now, if I took any two individuals from the population, if I had a really tall woman and a short man, the woman may have the higher lung capacity because it's more about body size versus gender necessarily. Okay. So what do we want to look at here? The biggest difference is, again, the IRV is the biggest difference, sorry, because that's the one that's the most directly related to lung size. The bigger my lungs are, the more I can inflate them and do a maximal inspiration. So typical vital capacities for men, 4.8 liters, women, 3.2 liters. And again, those are healthy adults. So again, here we talk about the factors that lead to males typically having a higher vital capacity. Some other factors though, age. Usually as people age, their vital capacity goes down for a few reasons. Usually tissue elasticity declines. So, your muscles are not as flexible as you get older, okay? Less flexible muscles around your rib cage equates to a lower ability to expand your rib cage. If you can really expand your rib cage due to flexible muscles, you can bring in more air, but less flexible muscles equals less flexible rib cage, lower ability to bring in air during a maximal inspiration. Muscle strength may also decline during as people age, and that can also reduce vital capacity. Now I'll say age alone doesn't produce this, but aging along with being sedentary really does exacerbate the situation or make it worse. If you stay active as you age and you force your respiratory muscles to work, you force them to contract and relax maximally, you're going to retain the elasticity and the strength in those muscles, and your vital capacity will not drop as much as you age, okay? So keep that in mind. Physical activity level trumps everything else, right? These age-related declines are worse if you don't exercise, but if you do exercise, they're not as bad. So that goes across the board for everything, not just vital capacity. So as you all get older, just keep exercising and your health will be maintained quite a bit better. Height and gender we already talked about, so I'll move on from those. All right, so let's talk about a test, and we'll do this in the lab this week. The most common test done to assess pulmonary function is known as the forced vital capacity test, okay? And this test is often used to assess a specific type of disease known as restrictive lung disease. Now, restrictive lung disease, as we'll talk about in a second, really affects inspiratory reserve volume. If you have a restriction that prohibits you from expanding your lungs, you're not going to be able to bring in as much air. The less air you bring in, the less air you blow out, okay? So this specific test is going to ask the person to breathe in as much as they can and then blow out all of their air into a device known as a spirometer, okay? And we measure the volume of air that they blow out in this maximal expiration, and that is used to assess their lung function, okay? As we'll see in the lab, we're going to ask the person to not only blow out hard, but also sustain their breath as long as they can, because that ensures they're emptying as much air out of their lungs as they possibly can. Restrictive lung diseases, as we see here, here are some examples of them. As I mentioned, restrictive lung disease limits your ability to expand your rib cage. So it's sort of like being put into a straitjacket, or maybe more something that's more relatable might be if somebody has you like in a bear hug and you can't breathe. So the diseases that would simulate that situation are pulmonary fibrosis, where your connective tissue around your rib cage has become very fibrous and inelastic, so it doesn't stretch well. Neuromuscular disease, where the muscles that assist in expanding the rib cage, they're not working properly, so you cannot bring in air. And then kyphoscoliosis is a condition that occurs in a lot of elderly populations, where people sort of get locked into this humpbacked posture. You probably all know old people who have this posture. Changes in their spine prohibit them from expanding their lungs. Because when you expand your lungs, you should get up nice and tall, right? But if you're locked into this position, your ability to expand your lungs is compromised. Okay, so again, less air in means less air out. So we measure the air coming out, and that directly reflects the amount of air that comes into the lungs. A second test, which we will not do on the lab, is this. Okay, so we call this one the FVC, forced vital capacity. The other test has a similar name, the FEV, forced expiratory volume. So what we're looking for with this one is the amount of air that comes out in a unit of time. In the unit of time that is the most commonly used is 1 second. Most of the air that we expire should come out in the first second of breath, right? When I first expire, most of the air comes out in that first second. I can continue expiring for 3 to 4 seconds, but the rate drops quite a bit, and this graph shows it. Usually the most air is expired in between 0 and 1 second, and then as the time proceeds along, the volume of air drops off a lot faster. This type of test is used to measure or assess for obstructive lung disease. So if you have an obstruction in your lungs, the air can come out, but the rate of flow is going to be slower. So imagine if you're trying to breathe out, and then all of a sudden somebody gives you a straw and you're trying to breathe out through a straw. You're going to get the air out, but the tube you're trying to breathe out from, that straw, is a lot smaller than your mouth, right? Which could be bigger. The straw is smaller. And that indicates you have some obstruction that is slowing the rate, the speed of flow. The volume of flow is not affected, but the speed of the flow is negatively affected. But that can be a limiting factor for exercise, okay? And you'll understand this when you see some examples of obstructive lung diseases. Asthma is probably the most common one, right? For some reason, people who have asthma, their bronchioles, those tubes that conduct air in and out of the body, they constrict. So a smaller tube means slower rate of flow through the tube. Again, think about the straw versus like a garden hose is bigger, a straw is much smaller. The water is going to move through either of those tubes, but it's going to move slower through the straw because the straw, it has a smaller diameter. Okay, same thing occurs when somebody has obstructive lung disease. Okay, with emphysema, we start to see these bronchioles are collapsing. Right, so you have less surface area for the air to flow through, so it's going to take a longer amount of time for it to get out. With COPD, chronic obstructive pulmonary disease, there is, what word do I want to use here? There's like crap built up in the lungs that also slows the rate of flow down quite a bit. So mucus, pollutants that get in the lining of the lungs. And think about it, if you have a nice open tube here, if there's a bunch of mucus that's in here lining the walls, the diameter that air can flow through is smaller because there's mucus lining the bronchioles, right? So COPD is something that often develops through for people who are long-time smokers, etc. and that reduces the ability for air to flow rapidly in and out of the lungs, and that would have a negative impact on exercise capacity for sure. So again, we measure these lung volumes using a tool known as a spirometer. Okay, and the one that we have in our lab looks a lot like this, and you all will see this on the video. Some instructions you would want to give to somebody prior to participating in a spirometry test we see here. Probably the most important one is the clothing, right? If somebody's wearing really tight clothing, they're not going to be able to fully expand their lungs. And that's critical for the accuracy of this test. You have to be able to fully expand your lungs. So you don't want to wear really tight obstructive clothing because that could have a negative impact on your ability to fill your lungs with air, and that would result in a low forced vital capacity test. So here's the procedure. The cue that is often given is to blow out 100 birthday candles. So imagine you have a giant cake in front of you and you have to blow out hard and sustain it. So, right? That will ensure you're getting all of the air out of your lungs, and that is the goal. As with most tests, we always give 3 attempts, and we take the best attempts of the 3 as the test value. I have a sample video that you all could watch, but you don't necessarily need to, because in the lab video for class, this will be shown. This is a different video that just kind of gives an example of what the test looks like. But take a second to watch that real quick if you're interested. So what we do though is we take these values that we obtain from forced vital capacity tests and we compare them to normal, right? So we have these charts that have been compiled and developed that tell us what a normal value is, and we compare an individual score to what is normal for their demographic population. So we see here some normal values for an FVC are about 5 liters. If somebody has a disease, either of the two, usually the volume is significantly reduced by about 40%. So we see significant reductions in the amount of air that somebody can expire, either maximally or within that 1 second, and that would indicate that they have some degree of pulmonary disorder. Okay. If you're using the FVC test, again, that indicates restrictive disease. If you're using the FEV test, again, that indicates they have obstructive disease. So you would use either of the tests. FVC assesses restrictive, FEV assesses obstructive. In our lab, we're just going to do the FVC and look for restrictive disease. Okay, our device does not have the ability to assess the amount that comes out in 1 second. So our lab is just going to look at the forced vital capacity test. Now, just to kind of put a bow on this and hopefully wrap it up here in a couple minutes. This could have a great impact, negative impact on exercise capacity. As we talked about way earlier in the lecture, our goal is to get as much oxygen in and as much CO2 out as fast as possible. If you have one of these diseases, that ability for rapid gas exchange is going to be reduced, right? And the less oxygen you can get into your body, the harder it's going to be for you to exercise, right? So if somebody has a severe restrictive or obstructive disease, their ability to do exercise is going to be greatly compromised. And that's what you would use this test to assess for, okay? Either of these would have a serious negative impact on an individual's aerobic fitness. However, if they started exercising, you could improve these numbers, right? And that's what you would do if you had somebody who had a poor test, is you would recommend them to begin an exercise program, and you would retest them and hopefully see an improvement in their numbers for these 2 tests. Let's see, what else do we want to talk about on this lecture? Kind of running out of steam here, and I'm sure you all are as well. What these next few slides show are, during exercise, how would we see some of these numbers change? Breathing rate refers to how many breaths per minute. Tidal volume, again, talks about amount of air per breath. During exercise, both of these go up. So not only are you breathing faster, but you're also breathing in more air per breath. So the rate we see here, usually at rest, we're breathing about 35 to 45 breaths a minute. During high intensity exercise, that increases to 60 to 70 breaths per minute. So we go on about a 1 breath per second. So, right, we're really huffing and puffing during high intensity exercise. Now, at the onset of exercise, tidal volume goes up first. So you start breathing more deeply. Then as we progress to intense exercise, then breathing rate starts increasing more rapidly. So VE changes initially due to changes in tidal volume, and then late it changes due to changes in breathing rate, okay? Let's see, and that kind of is shown here. Rest, moderate exercise, intense. Rest, moderate exercise, intense. But ultimately, these are both going to combine to increase the amount of air. Look at this. At rest, 6 liters a minute. During intense exercise, we're moving 150 liters of air a minute in and out of our lungs to help us, again, prohibit some catastrophic change in our pH, right? Since we're producing so much hydrogen and CO2, we got to get it out. So that's why we start moving just like a crazy amount of air in and out of our body compared to what we're doing at rest. Take a minute to read this slide, pause it now. Okay, I'm back. I already talked about this a little bit more, but that kind of shows the differences between the breathing rate versus the tidal volume, moderate exercise versus intense exercise, okay? So that's gonna do it. I know that was a lot of information. You might even want to go back and listen to this lecture again, okay? We have our study questions. There's only one video clip for this week. It's only about 10 minutes long. It's not too long at all. Now I go into some things in the lab that we didn't go into today or in this lecture. Mainly it's that we have to correct for the air around us as we do the test. Now, as we talked about with regards to VO2 testing, the air temperature, the air pressure, and the humidity affect the concentration of oxygen and CO2, right? It also influences the amount of air that we are expiring. So before we can compare our test results to the norms for that population, we have to correct for the environmental conditions. So in the lab, I do this really long equation to calculate how we need to correct the answer. I give you the answer in there, so just write down what I calculate. And then what we do is we take the norms for our population and we compare our corrected test result to the norm for that population. Okay, so again, in the lab, I go through this all kind of writing it on a whiteboard. All I really need you all to do is sort of just fill in the numbers that we call out, okay? If it's confusing to you at all and you want to ask me about it, just please email and ask. I'll be more than happy to explain it, but it is something that's a little complicated. I don't think it's anything you all need to really fully understand right now at this point in your careers. But just again, as I said earlier at the beginning of the lecture, I just want you to kind of get like a surface level understanding of how the pulmonary system works and then how we can test to see if that system is working properly, effectively, and then how we would compare test results to norms. Okay, so that's it. Coming in a little over an hour. This was a long one, but again, I dropped down 150 slides to 40, so an hour. I don't think that's too bad for 3 chapters. Hope you all are doing great, and I'll come back and talk to you soon.